function is continuous if there is no break along the path of the function. And these breaks includes holes, jumps, or a gap. So if I have a function graphically like this, where the horizontal line here is my x-axis, this is my y-axis, and this is my function. As we can see, there is no break along the function. So at every point, my function is continuous. A function is continuous if and only if these three conditions are met. Condition 1. F of a must be defined. And criteria 2, the limit of f of x as x approaches a must exist. And for third criteria, f of a must be equal to the limit of f of x as x approaches a. And these are our three conditions. Now, if I have this function here, where this is my x-axis, this is my y-axis, and this is my function. At this point, a, we can see that there's a hole in the function. So we say that this is a hole discontinuity or a removable discontinuity. Now, if I have a function like this, and this is my x-axis, this is my y-axis, and my function is this, where this point here is B and this point is C. At A, this function jumps from B to C. So this is known as jump discontinuity. For another type, if I have a function like this, gain my x-axis, my y-axis, this time I have a vertical asymptote. This vertical asymptote could also be the y-axis. So this white line is my vertical asymptote. If I have a curve like this, and that's my function, then there's a gap in between the functions because the white line is the asymptote, so it never touches that line. It goes up to infinity. This discontinuity is called infinite discontinuity. For this discontinuity, the removable discontinuity, as the name suggests, we can remove that discontinuity. So whenever we have a hole, we can remove that. So let's look at an example where we can remove the hole. Say you're given this function, f of x equals x squared minus 16 over x minus 4. And you're to test if this function is continuous at x equals 4. So if I'm supposed to find the limit of this function, f of x, as x approaches 4, if I directly substitute 4 in the numerator, I have 16 minus 16 over 4 minus 4. And that would be equal to 0 over 0, which is indeterminate. So we see that we have an indeterminate value here. And at 4, our function is discontinuous. So how we remove this discontinuity is by simplifying this before we substitute our value. So if we look in the numerator, we see that we have x squared minus 16. 16 can be rewritten as 4 squared. If we rewrite that, we would have x squared minus 4 squared. And looking at this, we see that we have the difference of 2 squares. So let's expand that. In the denominator, we have x minus 4. These cancel, and we are left with x plus 4. Now when we find the limit of this, x plus 4, we have 8 for our limit. And now our limit is defined. And that is how you remove a removable discontinuity. In a case where you would have an infinite discontinuity, would be a case where you have something like, you'd have a function like 1 over x. Graphically, 1 over x is shown as this, where our curve is asymptotic to our y-axis, and it never actually touches, so this goes all the way to negative infinity, and this goes all the way to positive infinity. So at this point, which is 0, our function is discontinuous. So x can never be equal to 0. And the same goes for other rational functions. So for example, x minus 3. We can never let x be 3, else we'd have 1 over 0, which would be discontinuous. It would be the point of discontinuity. So for a function like this, 3 would be the point where the function is discontinuous. Now let's look at jumped discontinuity. As we drew earlier, we saw that our jump discontinuity is something like this, where we have a function that's going on, then it jumps to another function. And these type of discontinuity normally comes in the form of piecewise functions. By the way, a piecewise function, if I never made mention to that, a piecewise function is a function that has other functions. These functions inside the piecewise function is based on different input for x. So this would be an example of that. F of x is equal to x plus 3 over 2 when x is less than negative 1, and x squared when x is between negative 1 and 2, and 2 when x is greater than 2. So this is what a piecewise function looks like. And we are supposed to determine if the function is continuous at the point negative 1 and at the point 2. So let's do this at x equals negative 1. The first thing we want to do is to test and see if the limit exists. How we do this, we want to make sure that the same value we get when we approach from the right is the same value we get when we approach from the left. So if we approach negative 1 from the left, then we would use this function. And the reason why we would use that function is because x here is less than negative 1. So we're approaching negative 1 from values less than negative 1. So we would have limit of x plus 3 over 2 as x approaches negative 1 from the left. When we directly substitute our negative 1, we have negative 1 plus 3 over 2, which is equal to 1. Next, we want to approach from the right, so we'd use this function. The reason why I would use x squared is because negative 1 is included in x squared, and this function includes values that is higher than negative 1 as well as negative 1. But we're interested in values higher than negative 1, so hence the reason for using this function. So the limit of x squared as x approaches -1 from the right, if we directly substitute -1, we would get 1, because -1 squared, let me do that, 1. So that's one test. We see that our function, the limit of this function exists and it is equal to 1. The next test we want to do is test to see if f of -1 is equal to this. So let's do that. F of x is equal to x plus 3 over 2. If we directly substitute our value for x, which is -1, we would get 1. So these two match. And for f of x equals x squared, if we directly substitute, again, as we see here, we'd get 1. So again, these two match. So since f of -1 is equal to the limit of the functions as x approaches 1, then we can say our function is continuous. So we can write our statement to say the function is continuous at x equals -1. Now we're going to test if our function is continuous at x equals 2. So we're going to approach 2 from the left first. So the limit of f of x as x approaches 2 from the left. When we're approaching 2 from the left, we'd use this function. And the reason for using this function is because the values are less than and are equal to 2, meaning that all the values here are from the left side of 2. So we're going to use x squared when we're approaching from the left. So our function would be x squared. So the limit of x squared as x approaches 2 from the left would be 4. And that is because we would substitute 2 for x, and when we square it, we'd get 4. Next, we want to approach it from the right. The limit of f of x as x approaches 2 from the right. Let's look back on our piecewise function to see which function we use for the right. If we look here, we see that this function is less than -1. We would use this function if our x value is less than -1. But remember, we want values greater than 2 because we're approaching from 2. If we look at this, this is values of x from -1 to 2. So we could not use this function. Now, if we look at this, we see that we're going to use values greater than 2. And this is what we want, values that are greater than 2, since we're approaching from the right. So we'd use 2. So the limit of 2 as x approaches 2 from the right would be equal to 2. And the reason why this is equal to 2 is from limit theory. Limit theorem says if you're finding the limit of a constant, then the limit of that constant would be the constant. So graphically, if you have the function 2, it would be something like that. So at every point here would be have 2 corresponding there. So that is the reason why the limit of 2 is 2, no matter what we are approaching. Now we see that When we approach from the left, we have a 4. When we approach from the right, we have a 2. This simply means that the function is discontinuous. But let's do the next proof, because we must do all of them when we are showing our working. So the next thing we need to do is to find f of a for this function and to find f of a for this function. For the first function, which is x squared, when we find f of a for x squared, when we plug in 2, we would have 4. So that's the same. But if we plug in f of a into the function for 2, this is the function, we'd get 2 because there's no variable here to plug into. So we'd still have 2. And even though these correspond to each other for their individual functions, this still would be discontinuous because the value we get when we approach from the left is different from the value we get when we approach from the right. When this happens, this means that the limit of the function doesn't exist at that point. And that is one of the conditions that must be met for functions to be continuous. So this function is not continuous at the point 2. And this is it for limits until we come back to L'Hopital's rule. Thank you guys for watching.